All right, so I'm going to record this and let's get started. So thanks for dialing in. And this is Research Methods for People in a Hurry. Sorry, Neil deGrasse Tyson, I'm stealing your book title, which I really did like. So quickly about me. Well, first, if you can remember anything at all from this, this ordeal, number one, you can only manipulate one thing at a time. And we'll go into exactly what that means, but if you're designing an experiment, you can have basically rows and columns, and you have to fill all your cells or have a good reason not to. If you manipulate two things at a time, you won't know which one of those things is the operative change, and you're gonna have a problem. The second thing is it's pronounced, Dr. Lickert's name is pronounced Lickert. Everybody seems to say Likert. It is actually Lickert. One of my professors was his student. She taught research methods, and now I'm teaching research methods. So I got to make sure that everybody gets it right. It's Lickert, like licking a lollipop. And the third important lesson is to pilot, test everything all the way through getting your data, because if you don't, something bad's going to happen. I had some colleagues who spent $500 a person running an MRI study and then found out that they did not record any of their data. So they spent a lot of time and money and got nothing for it. So pilot. Quickly about me, I earned my bachelor's in human factors and a minor in psychology from Cornell. I worked in ergonomics consulting and probably did some research that wasn't very good for a small company with a big name called US Ergonomics. It was first 2 people, then 3 people, so small. I got my master's degree in persuasive interface design at New York University. Basically ran a large interface design and psychology type study for my master's degree, and learned some more painful lessons about research design. And then I got my PhD in communication research at Cornell, or not at Cornell, at Stanford. I was a postdoc at Cornell. I taught there, and then now I am a postdoctoral scholar at the University of Central Florida. So research can kind of be put into 2 main traditions. One is qualitative and one is qualitative. Qualitative and quantitative. Qualitative is sort of, as the name would suggest, like qualia. You're trying to look at things in a holistic manner. Things like anthropology is mostly qualitative research. Ethnography sort of goes under that qualitative research banner. Quantitative research, like the root word quanta, you're quantifying or counting things. So if you're doing, say, a survey where people are marking things off on Likert type scales, or you're coding data in some way where you're saying, all right, how many times do people press the button? Or you've got people doing a test where they have to pick left and right, that's quantitative. And so if we think about the types of research that you can have observational research where you're just observing things and not manipulating anything. Sometimes there's an inevitable manipulation. So if you think of an anthropologist going and meeting with a minimally contacted group of people, by their mere presence, they're influencing people's behavior, but they're trying to not systematically manipulate anything. There's experimental research where you're actually, the point is to manipulate something. So you say, I'm going to give half the people a placebo and half the people aspirin. That's a manipulation. And then quasi-experimental research, as you might guess, falls in between. So things like a natural experiment where you're not systematically doing random assignment to groups, or doing matched sets or anything like that, that goes under quasi-experimental, and you can split a lot of hairs when you're arguing with the real research methods people about whether your study is a true experiment or a quasi-experiment. But want to just sensitize you to those things. So we talked about the techniques a little bit. So under the quantitative side, you can have experiments, you can have surveys. And then under the qualitative side, you can do interviews. There are more and more sophisticated techniques to do data mining or text mining. You can have people do a speak aloud. So you can ask people to go and walk through their behavior and using a website or something like that, or speak aloud. And so they're saying, I'm going to go and click on the green button. Oh, now I got a new page and I got the red buttons and I can read the text. Things like cognitive task analysis are sort of under qualitative. Observational research is generally sort of under the qualitative side. So there's a lot of things in there. Regardless of which side of things we're going down, you have to come up with a set of research questions. And basically, they have to be worth the investment is kind of the first criteria. So you think about your corporate sponsor or National Science Foundation, or even just yourself. Is it worth the money and time to ask this question? Am I going to get something worthwhile out of it? So I spent for my dissertation a couple thousand hours sitting in the dark watching people automate, like in a driving simulator. Was it worth my time? Some of it was and some of it wasn't. But I had to go and do all these things. So that's part of this calculation of the investment. Certainly, if you're doing experimental research, you want questions that are empirically testable or observable. If you want me to go and tell the story of the N-rays, I can, but you can't go and say that there's an invisible gorilla in this room when there's no way for me to go and demonstrate or test whether there is or there isn't. And that also, we'll talk about that a little bit more on the next slide, which is about hypotheses and developing those. And then your research question has to lead to some way to assess at least correlation or causation. So as we're developing hypotheses, we want to go and say that A causes B, or X causes A and B, or at least just A and B occur together. So I just want to pause for a moment, see if anybody has any questions.
I have no question. Please go on.
Okay. Okay, so we want our hypotheses to be specific. If your hypothesis is overly broad, it's going to be hard to go and say like that this is something that can actually be tested or can be falsified. So if we're thinking about Lisa and her tiger repelling rock, we'll go through this in a moment here.
Not a bear in sight. The Bear Patrol must be working like a charm.
That's specious reasoning, Dad.
Thank you, honey.
By your logic, I could claim that this rock keeps tigers away.
Oh, how does it work?
It doesn't work.
Uh-huh.
It's just a stupid rock.
Uh-huh.
But I don't see any tigers around here, do you?
Lisa, I want to buy your rock.
Okay, so we can say that there is a specific hypothesis about this rock repels tigers. It's also a testable hypothesis because if we went to the tiger cage and the tiger ran away, that's how we could test it. It's falsifiable in that if the tiger doesn't run away and mauls us, our rock does not work. So it kind of meets the criteria if we set up our experiment the right way. Now, the problem that Homer has is that this is framed in a negative way, not a positive way. So you can't prove a negative. You can't prove that the rock keeps tigers away if there aren't going to be any tigers there to begin with. So, I mean, you can make claims like, so to go down the rabbit hole a little bit, and hopefully I won't mangle this story too much, but back in the early 1900s, everybody was looking for rays. So there's the gamma rays and X-rays, and this guy Blondlow is a physicist. He says, there is the N ray. And so he builds some sophisticated equipment and says that the N ray exists, and his equipment picks it up and shows things on a photographic plate. So he gets, I believe, Thomson, the eminent physicist, to come. It's either Thomson or Rutherford, comes to France, and our eminent visiting physicist pulls a piece of the machinery away surreptitiously. The photographic plate is still exposed. Blondlow says, see, here's evidence of the N ray, and our eminent visiting physicist says, would your system work without this piece? And he says, no, it wouldn't. And he says, well, then it's been in my pocket the whole time. You have now no Nobel Prize for you. But we can't say definitively that there is no N ray. We can say that we did not find it. We did not find evidence for it, but we have not proven that it's not there because we can't prove that something doesn't exist. If we frame our hypothesis the other way, which is that the traces on the photographic plate demonstrates that there is, we can demonstrate that we didn't find it because our system doesn't work. So that kind of, does that explain adequately this idea of falsifiable and positive framing? Okay, I'll go on. So when we're talking about variables, we have our independent variables, which is things like our starting conditions, things that we can measure about the participants or the qualities of a device or the quality of concrete. And independent variables also covers the factors that we can manipulate. And dependent variables are the things that we can measure that are outcomes. So to talk about my dissertation on human-computer moral conflict, we have survey measures, which is what do people want a system to do. We can go and randomly assign people to computer behavior. And we have the various parameters of our situations as a repeated measures design. And then our dependent measure is how much do people fight against the system? So they're driving in the driving simulator. How much do they turn the steering wheel against the computer, which is pushing them one way or another? The goal of an experiment is to establish the arrow of causation. So if we have A and B, if we're doing correlational research, we can say that A and B appear together. A could cause B, B could cause A, something else could cause them both. But how do we demonstrate that A causes B and not some latent variable X causes both of them? An experiment can do this because if I go and I say that I give you A and that causes B, but I never see B independently, then I can go and maybe go and test some other things like nothing else causes B and nothing else specifically causes A. Now I've established that A causes B. So when when we're talking about these ideas, these theoretical constructs, so and then we need to translate that into an operational measure. So if I have a concept of, say, trust, I mean, there's a big area in human-computer interaction, driving systems, robots. We have this concept of trust. But what is trust? Trust has a bunch of definitions. Trust has various ways that it can be expressed. So we have to make operational measures. So we can go and give people a survey and say, how much do you trust this? How much do you believe that it is capable? How much do you believe that it is working in your interest? We can give them a survey. We can also test trust by reliance. So if anybody knows that the trust fall, so you go and you have somebody behind you and there's nobody here. So you have the trust fall, I lean back and somebody's going to catch me. I'm demonstrating that I trust them. You can do the same thing with a robot. So if I go and I say, all right, I'm going to trust this thing, I've demonstrated behaviorally that. And if I put these things together, I have a much better measure than necessarily either one alone. So for manipulating things, what we want to do is we want to make sure that we can establish that causal claim. So this is for a real experiment, not just correlational research. So we want to manipulate things. So we have an initial condition, and we want to say, well, we have a manipulation. Does the manipulation cause some outcome? And we often have a control condition. So we say, all right, people who are in the initial condition, they end up the same in the control condition because we haven't given them the active treatment. Often with these, we want to do what's called a placebo-controlled test or placebo-controlled trial, where we give people something in the control condition. So if I'm testing the COVID vaccines, if I go and I give people the COVID vaccine here, and then I measure, do they get COVID? I don't want to compare them against people who haven't gotten anything. I want to compare them against people who have gotten some other shot so that they think that they've got the COVID vaccine and behave the same way. So I give half the people COVID vaccine and half the people something else that makes their arm sore. And now we have a way to go and make comparisons. And we can see the results here. So if we're doing this, we have our initial condition. And in the ideal case, people have the same, say, rate of COVID at the same time, at the beginning. So say that the test positive rate is here. The people who get the placebo, their test positive rate at the end is the same. The people who get COVID vaccine, their positive test rate goes down. And we can say that this is at least effective. Now, of course, things get complicated in real life, and we often have more than 2 conditions. We might have 3, and things get complicated. So if we're looking at the independent variable, we have 2 independent variables here. So one is the strength of how much I tap you with the hammer, but I'm not exactly great with my hammer tapping. That could be a continuous measure of the hammer tapping. So I had to put a force sensor on my hammer, and now I've got a covariate, and it makes for a complicated experiment. And I have a categorical, so categories of whether I give you the drug or which one. And that leads to sort of complicated outcomes, and it becomes a little bit of a mess, but we have statistics to deal with this. What we would want to do is have basically something that's like a crossover design and look for this interaction effect. So say that I systematize my grandpa hammer tapping to hard and soft, and I have 2 drugs. I can then say, all right, if I give you a hard tap and the drug that doesn't really work that well, the bad drug, your pain level stays high because you're already at the ceiling. There's a problem because there's something called ceiling effects, where people are, they don't go any higher. If your pain level is 10, there's no higher. If I give you a light tap and the good drug, you barely noticed here, and it only got a little bit better, so you're at what's called the floor. So you're going to say, well, it's a 0 on the pain scale, and then I give you the drug, and you're like, my pain level is still a 0. But if I give you a light tap and this bad drug, now your pain level goes up, and the FDA is going to come down on you like a ton of bricks. If I give you a hard tap and the good drug, then your pain level is going to go down, and that's what we want to see. So this one gets approved and this one gets recalled. How's that sound?
I think the example of pain level 10 is actually very good because almost anyone can relate to that.
Let's hope that I don't actually go around giving people taps with the grandpa hammer that lead to pain level 10. I don't think the IRB would be happy about that.
No.
Yeah, we should talk about the IRB, but we'll get to that later. So we've got our experiment designs, and we can do these in 3 ways. There's only 2 on this slide because of room. So we can have a between participants or between conditions study. And the benefit of this is we don't get carryover effects. So if I go and I have my 2 pools of people and I give them the hammer taps, there's no interaction between them, and there's no effect of, well, I got the light tap before the hard tap or the hard tap before the light tap. So we don't have things carrying over where people are comparing against their previous condition, things like that. The drawback is that this means that you need a lot of participants, and you have a lot of variation in individuals. So you need a lot of participants to try to wash that out. Because so to think about this, if we get 100 people, a couple of those people are going to have chronic pain diseases, and a couple of people are going to be pretty insensitive to pain because they're used to getting whacked all the time. So we want to have enough people in our sample or enough experimental units that doesn't become a systematic problem. And what we want to do to reduce that threat to validity is random assignment. So in the ideal world, if we randomly assign enough units to our groups, then we will not, we're unlikely to have systematic bias. We can also do matched groups. So if I'm getting people for a study of how much can people go and pull the screws out of that bracket on the wall, if I randomly select UCF students, that probably would work okay. But say that I have a limited budget or a limited access, I put people in my conditions systematically, so I get a couple of basketball players and a couple of short people in each condition, because otherwise randomization wouldn't work if I only had a few. Within participants has its own benefits and drawbacks. So the benefit is that it can require fewer units, but it's not guaranteed, because if we have to worry about counterbalancing and accounting for order effects, then you can quickly end up with needing just as many or even more people. The benefit is that you can measure effects over time, so you can do a longitudinal study. These are very popular and necessary in education, in medical research. Like there's a really incredible one where Harvard ran a study for about 80 years on, they said, all right, we're going to take the class of 1920 and we're going to go and interview these people and track what happens to them. And one becomes president and then gets shot. Some of them become titans of industry. Some of them become homeless. They just keep measuring, and they've got all this data for a long time. the drawback is that we have to worry about these carryover effects. So you could have a training effect where people get better at something over time. You could have a fatigue effect where people either get annoyed or bored or just fatigued. I mean, imagine that you're measuring how much can somebody bench press. Their first one, they could bench press a lot. By the 10th rep, not so much. And you can have context effects. So the environment has an effect on people or other physical properties as well. And these can vary over time. And that can become a problem because it can contaminate your data if you have some event occurring in the world. And that goes and screws things up, especially if it happens to one group as opposed to another group. And there's all kinds of methods that you can use, like counterbalancing. Latin square is a commonly used technique for partial counterbalancing. It doesn't solve all of your problems, but it can solve some of them and reduces the complexity by quite a lot. So if we have a simple experiment, and in the immortal words of my PhD advisor, Byron Reeves, the secret to getting tenure is 2x2 experiments. So our simplest experiment would be a 1x2, but if we make a 2x2, that gives us a lot of abilities without too much complexity, and we can analyze all kinds of things from it. So we have manipulation A and manipulation B, and we end up with 4 cells. So for a more concrete example, we have we're building a bridge and we have a limited amount of time to build the bridge. So I can buy normal concrete and quick setting concrete in 2 different strengths. So there's regular concrete, regular strength, and extra strength. So if I have normal setting concrete and it's regular strength and I don't give it enough time to set, I get gloop. That's not going to make people happy. If I have extra strength, normal setting concrete, and I still don't give it enough time to set, it's still gloop. If I buy quick setting concrete, and that comes in the regular strength, I get regular strength pylons and everything will be great unless I overload my bridge. And surprise, there's no such thing as extra strength, quick setting concrete. So we're out of luck. We have an empty cell. And this means that we can't look at interaction effects, but this is still a common thing that happens. Any questions?
In my mind, when I think of a 2x2 design, I think of running like chi-square tests and things of that nature. It's part of the benefit of it having easy, repeatable hypothesis testing. So you're like, hey, I know I'm going to run this hypothesis test. I know how to interpret it. I know how to write it, and it's just quicker.
That's one of the benefits. The other benefit is that you can look at interaction effects. So if you have continuous variables, you can use an ANOVA, or more sophisticated ones like an ANCOVA, which adds a covariate to your ANOVA. You can obviously use regression as well. If you get things that are more complicated, then you can kind of analyze like a 3x2 and still talk about interaction effects. Past that, it becomes almost impossible. And too much past that, it becomes actually impossible to talk about interaction effects in any systematic way. So it's like, this is the easiest way. And to address Sean's comment about chi-square, if you have counts, so say number of pylons that are up to strength, that is what you would use a chi-square or Fisher's exact test. If I'm measuring the crush strength of my pylons, that's a continuous outcome. My Instron machine will go and give me an exact value of how much it takes to crush, and that would be analyzed in this case because we're comparing multiple things. We'd probably use an ANOVA. So for a slightly more complicated design, this is a mixed design, which has a between participants factor and a within participants factor. So say that I'm testing trust in an automated driving system. I've written several papers on this. And this is the design from my friend Ernestine's latest paper. I was one of the authors on that. So we give people a survey at the beginning. How much do you trust a theoretical automated driving system? And people go and they indicate their level of trust. And then we have an intervention, and then we give them the same survey again. So how does the intervention influence their survey results at the end? We also have another set of measures, which is their actual behavior. And that allows us to do what's called triangulation. So we can say that their survey results after also does vary systematically with their actual trustworthy or trusting behavior. Now, we have 3 levels of our variable that's between participants. So everybody gets either a perfectly performing system, an untrustworthy system that misses things, so it just stops working and drives off the road, or we have a system that has false positives and it jams on the brakes when there's nothing in front of you. And so we can see what happens in an interaction between these. So we could say that the what's their trust after they get false positives? How's that different from their trust when the system misses? How are each of these different? And so we can have multiple comparisons, and we have to use an ANOVA for this because we want to make sure that we don't have accumulating false positive errors from multiple comparisons. And that's something that trips up a lot of people because they're like, oh, we're going to go and do a bunch of paired tests. But once you start doing paired tests, you can end up with accumulating errors. And we're going to talk about that in very brief terms in a little bit. And this is what's this is a repeated measures design. So this is my dissertation. And we have people doing a set of events in sequence. If I had lots more time, lots more money, I could have gone and changed the order for people so that the truck does not influence the tractor, does not influence the car, does not influence the other truck. But I had to go and say, for economical purposes, that there's only one order for the people. And so these things happen in sequence. And we can measure what happens, and we use a repeated measures ANOVA, or in this case, repeated measures ANCOVA, which adds in a covariate, to see what happens to their behavior in 2 different conditions and all of these experiences over time. And there are more sophisticated measures that you can use, like time series, to go and look at things over time if you have to think about these issues of serial order effects and stuff like that. So to talk in brief about the Latin square, which is a clever way to be a little bit more economical with a repeated measures design, you rotate through which things come first, second, third, fourth. So if I have order 1, it's A, B, C, D, and then some people get order 2, B, C, D, A. The drawback to this is that B is always after A, and D is always after C, except for the things that happen last. So it doesn't completely get rid of the carryover effect of, say, C influencing D. But otherwise, we would need a lot more orders to do a full all of the possible orders. And that would mean we'd need lots of people and get really expensive. How's everybody doing with this? Okay. So when we're talking about samples, in the ideal case, we want to have a representative sample, and ideally one that is large. You can get into trouble if you have enormous samples because it overpowers your experiment. We'll talk about that in a moment. But most things in life that are measured continuously end up in this normal distribution, whether it's filling the beer bottles, the story of how the normal distribution and the student's t-test was developed as the product of the Guinness Beer Company is fascinating. But basically, a lot of things are distributed like this, whether it's beer bottle filling or height or things like that. So what we want to do is we want to make sure that we have data that's normally distributed, especially at the beginning. So if we go and we say, we ask people, how much would you trust this theoretical automated driving system? We might hope that it's distributed like this, but it might not be. It might be that everybody says, oh yes, I would trust this thing a lot. Or people are like, I wouldn't trust this thing at all. And then we have to use different statistical tests. We might have to redesign our experiment. But for our sample, and especially like people doing large scale research, you often end up with things that get normally distributed as you get more and more units. So statistical power is a concept of how much are people how many experimental units do you need to detect a certain size of effect. So most statistics have a measure of effect size. And this is from a piece of software called G-Power, which is free and easy to use. And this is just the output for a t-test. So comparing two groups, a paired t-test. So if I have a very small effect that I'm trying to detect, I need almost 800 people to pick it up. If I have a really big effect, I only need 30. So that ideally we would have a measure of our estimated effect size as we're going in to say, how many people do I need to pay for? So if I'm saying, all right, I've got a medium effect size of 0.3, I need 90 people in my study. A lot of the better journals are now requesting or requiring a priori power analysis. So especially if you are going to pre-register your study. So if you're going to do something in health, psychology is increasingly wanting people to do pre-registration. You have to go and say, based on the previous literature, the effect sizes are somewhere in like, say, the 0.3 range. So I'm going to go and get 90 people. And so I have a reasonable likelihood of picking something up if it's there and rejecting a false positive because I don't have far too many people. So if you think about Jeff Hancock's study of the effect of changing the level of positivity or negativity in your Facebook feed, the effect size that he was looking for is tiny, and he could get 70 million posts on Facebook to analyze. So he could say, we have detected a statistically significant outcome of the valence of your Facebook news feed. The practical significance is almost nothing for an individual. So he's like, all right, I've got a tiny effect, so that's going to be like way up here. And you can people can go and come after you for an overpowered experiment where you end up saying like, oh, I've got a tiny effect, but lots and lots of units. So this is it actually practically significant versus statistically significant? You can also, using tools like gpower or your favorite stats package, calculate your achieved power. And that's something that's good to report. So you can say, we had 90 people and we achieved our power target. And if we look at this, so we specify that this is two-tailed. We think about that. This has two tails. If we know the direction of the target, what we expect to have happen, we could say, all right, we're going to throw everything in this side, and it makes it easier to get more power out of our sample because we're not dividing it in half. The other thing on here is we set this alpha probability, and 0.05 or a 5 in 100 chance of a false positive is just something that's generally used, mostly because this is a nice round number. There is nothing magic about 0.05. If you think that it's valuable to have a lower threshold, you could say, I'm going to use a threshold of 0.1, a 1 in 10 risk of a false positive as opposed to a 1 in 20 risk. And then the other part of this is power, which is your risk of a miss. So if there's something there, you have a certain likelihood of not picking it up. People often use 0.8, so 80% power. You can increase this. So some people might say, I want a 90 or a 95% power, but that screws with the balance between a false positive and a miss. So you have to balance these things using kind of your intuition and your friends who have been through this before, in terms of saying, all right, what's the risk of a false positive or a miss? How's this sitting?
Something I always think about, Dave, in regards to these is the idea that I don't know, it's like the sanctity of is p less than 0.05, whereas I know in human computer interaction there's a group of people pushing for the idea of like, hey, if p is 0.06 but the effect size is very large, isn't that really important to talk about, especially in certain contexts like medical or health? Like, so for example, like, what if you're like, oh, the Moderna vaccine doesn't work, it's only, it's 94.1%. Or the Pfizer's 95%, so that's okay.
Yeah, this has been an issue of debate all the way back to shoot, I'm forgetting exactly which of the famous cantankerous statisticians was the one who like picked 0.05 and then was on record. He's like, there's nothing magic about this. It's just a number that I picked. So part of it is the practical significance that you have to factor in. The fact that journals are starting to be like, oh, just having a statistically significant result doesn't really mean anything, because you could have a statistically significant result, but it doesn't
True.
mean anything in practical terms.
Yeah, I've noticed that too. I've noticed that shift more consistently reviewing papers and also in submissions and how people interpret things. But I haven't quite seen it yet. I've only seen one paper where the author really was like, hey, like they presented a lot of these results with medium to large effect sizes, but p was like 0.07, 0.08.
Yeah, I mean, I think it's totally legitimate to say that if your effect size is large and the practical implications are large as well, there's nothing wrong with using like even perhaps a 0.10. And then on the other side, you could say extraordinary claims require extraordinary evidence. So if I'm making a claim that is that I want to be really sure about, I would want to use a much smaller alpha and say I have a very small risk of a false positive, making a claim that something that's potentially dangerous or major policy implications or something like that.
Yeah, on the flip side of that, I had a paper last year where we did Bonferroni correction, and we also stuck with something where, like, we didn't do Bonferroni correction where alpha was 0.05. We did it with alpha is 0.01. And that was because of it was a naturalistic study in a classroom, so the data was so noisy. And we're like, if we want to make claims with this, we want there to be a very high percentage. But it also, those are all, it was a collection of like smaller effect sizes. So like we were using Cohen's D, and everything was like between 0.2 and 0.26.
Yeah, so that's like in here.
Yeah.
So for the people who are going to be watching the video, I'll flip ahead a couple and just quickly explain these things of, so Bonferroni correction is one of the things that you can do after an ANOVA. So say that I have my 2x2 study or more complicated design. I can't just go and do multiple comparisons because I will increase my risk of a false positive. So the generally accepted method is use an ANOVA, which gives you an omnibus test of, is there something significant to find here? And then if there is, then you can use either planned comparisons. So it's like, all right, I think before I've looked at any of my data that I want to compare these two things just by themselves. That reduces your risk of a false positive. Or you can use various mechanisms that protect you. So they're called protected t-tests. So if I'm protected by my ANOVA, and then I adjust my degrees of freedom in the post hoc t-tests. So Bonferroni, Tukey, HSD, there's a bunch of other ones. They are accounting for this risk of accumulating false positive rate. Bayesian stats, which I don't really know much about, have ways around this, but that is something for another discussion with somebody who actually knows about it. And I mean, we'll get to this slide in a couple, but I want to go back in time and talk about validity. I really should have put Validity Hawk on this slide. So Validity Hawk is an actual hawk that flew into my lab and stared me down with its beady little eyes from the rafters and was like, hey, you ever gonna finish your dissertation and you're gonna get this right this time? So yeah, beware Validity Hawk. So there's 4 big categories of validity and threats to them. And there are a bunch of other ones. So if you want to go down the rabbit hole, you can read Shadish, Cook, and Campbell's seminal chapter on this. There's plenty of other discussions of validity, but we're just going to skate across the surface for the moment, and then we can talk about these. So internal validity and ecological validity are like the 2 headline things. So internal validity is how well are we measuring the things that we are purporting to measure. So if I'm measuring trust, so trust in my robot, how good is my measure? So if I give people John Besançon-Drury's well-known, well-used measure, it's probably going to be at least a reasonable assessment of the actual concept of trust. How good do these measures hold together? And there are the threats to internal validity, which is that I could have things that are confounded. So the appearance of the robot actually influences people's impression of how trustworthy it is. That is a potential problem. There could be noise in my experiment, so the robot might not be completely repeatable in its behavior. This is one of the great things about simulation or using robots as opposed to actors. You can have perfectly repeatable experiments. If you have a lot of noise from the outside, if you have longitudinal studies, things in the world can go and screw with your internal validity. So if I'm measuring how well people think that the US government does in terms of its intelligence gathering, and I do my first survey deployment on September 10th, 2001, if I do another deployment on September 12th, there's been a big change in the world, and that's going to mess with my data, and I can't compare them. So I now have to go and be like, oh, shoot, I got to go redesign my study because it has been influenced by history. Ecological validity, and some people call it external validity, and there's debate about whether you can call it external validity. Some people get really annoyed about that. How well does our research represent things in the real world? So if I go and have a future design thing, how well could this actually exist? That's a question. When people go and they run studies in a psych lab, how much does, like psychophysics, where people are like, okay, you have to, like, how long does it take you to detect the block that is rotated 90 degrees in a field of blocks? And you're in a nice cold lab, and there's an EEG thing on your head, and you're just sitting there staring at the screen. How does that reflect things in the real world? That's a question of ecological validity. So it's like, okay, people can detect the rotated block faster because of some, like if I give them amphetamine, I mean, this is a study that people have done. But in real life, are people going to be taking amphetamines, and are they going to be like looking at blocks? Very rare. So that might have quite a lot of good internal validity. It's perfectly repeatable. It's controlling for everything, but it's not representative of any actual task. And there's this concept of construct validity. So are you studying the thing that you actually say that you're trying to study? So say that I'm doing one of these block rotation tasks. Am I testing how well people can do mental mental rotation, or am I testing something else? So if the am I doing a good job of controlling out things that could go and screw up my construct? So if my construct is mental speed, and the block rotation task actually doesn't study that, you've got this extraneous variable of how fast you can look at things, the brightness of the contrast of the screen, things like that. My construct might not be valid. That's probably a bad example. Let's see. So if I have a theoretical construct of the trust one's an easy one. So we've the trust in the robot, and so we have this concept of trust, and we operationalize it with a survey. What people say isn't necessarily the same as whether they would actually trust it. It's what they say they would do. So we're losing construct validity in that case, because there's a big difference between what people say and what they might actually do. And that's why we use concepts like triangulation, where we have multiple measures So it's like, okay, we test, what did they say? They say that I would trust the robot. Do they actually trust the robot when the fire alarm in the building sounds and the robot says, I'm gonna guide you to the exit, but then starts driving the wrong way. And you're like, wait, the exit sign's over there. Why is the robot going that way? Do I actually follow the robot or do I follow the sign? There's actually a study people have done. Nobody was actually killed in that study, but they did a great job of making it look real. And then our last big category of validity and validity threats is statistical conclusion validity. And that's basically, are you using the right type of statistics for the data that you have? And I was eternally embarrassed in this case. So I went to my first real conference and had a bunch of count data and was using a t-test to explain it. Guess what? T-test is not the right kind of statistical test for this. And someone who is now one of my great friends, Beth Carlin, this is for you. She's like, hey, you're using the wrong statistical test. Because you have counts, you need to use a chi-squared test, not a t-test. So other than embarrassing myself, almost ended up in big trouble. Good thing I then took more stats classes and actually learned stuff. But you want to be using the correct type of tests and the correct model for your research, because otherwise you might be like, oh, there's no way to explain a four-way interaction. There is no way to deal with these kinds of problems like non-independence. So my master's thesis, one of the problems is that because people's behavior is not independent, when they're washing their clothes, turns out people go down to the laundry room and wash 2 loads at the same time. That's not independent. And t-test or chi-squared test or Fisher's exact test, ideally you have independent samples. So it's kind of confounded in that way and not ideal, but we got through that. My committee signed off, I've got a master's degree. So to talk about this types of data, you can have continuous data or you can have discrete data. And so continuous data is like the weight of something. I can put it on a scale and I can get infinitely fine with my measures. I am 39 and a bunch of days and a bunch of seconds old. That's continuous. So if I'm comparing things, I can, and my data is normally distributed, that means that the errors are also normally distributed in theory. And so I use things like a t-test. If I have pairs, I use a paired t-test, and ANOVA, repeated measures ANOVA, ANCOVA, multiple ANOVA. These are all requiring normally distributed data. If I have skewed data, so it turns out that I have a floor ceiling effect, which we don't want to have, but happens in real life. We can use things like Wilcoxon, non-parametric ANOVA, regression kind of can be used on this side. And then if we have discrete measures, so counting things like how, like, so the t-test was developed to quantify and beer bottles. So how full are the beer bottles coming out of the Guinness plant? Over here, if we're counting the beer bottles, so the number of beer bottles in a case. So say that our beer bottle packing department, we've got some sticky fingered packers. There's supposed to be 6 bottles of beer in each 6-pack. If I go and I do an analysis of how many beer bottles are in the pack, it could be 1, 2, 3, 4, 5, 6, 7. That's discrete. I can't have half a beer bottle. So that I would be using a chi-squared test. If I have a small number of samples, I can use Fisher's exact test, which is slightly better for small samples. If I have pairs, like I have 2 different packing lines, I would use McNemar's test. Chi-squared test can also be used for more than 2 groups. And then of course, there's a whole Bayesian thing that's like way beyond my pay grade. This is a reasonable introduction to the like picking statistics flowchart.
Yeah, yeah. What I've started to do is actually code my own thing in Python, where you just feed a CSV through it, and then it will kind of tell you which one to do, which is a great way to kind of get this stuff stuck in your head.
That's pretty clever. Often you would go and like if you're trying to write an analysis plan, it's good to go and figure this stuff out ahead of time, especially as people are now more often asking for pre-registrations. If you're writing an experiment proposal for your dissertation, you got to be like, all right, I'm going to get this kind of data, and this is the kind of outputs I'm going to use. Although, like, you may not know whether your errors are going to be normally distributed or not until afterward.
Yeah, I always found it useful to look at your research question and study design and know well ahead of time, before you even do anything, what test you're going to actually run. Which leads you back to the whole 2x2 design.
Yes.
It reduces this. This is usually, if you have to do this after the fact, is usually pretty mentally exhausting.
And then you realize, oh, I should have done this thing in a different way 3 months ago, and that's not a good feeling. So one of the things that is a big thing often paired with the behavioral measures is surveys. Obviously, surveys are used on their own for all kinds of things. So there's some helpful hints in survey methods. I mean, you could take an entire class in survey methods. One of the biggest issues is avoiding leading questions. So you don't want to ask people, how much faster did you read in font 2 than in font 1? Because people are going to be like, oh, they're asking me if it made me faster. So it's like leading the witness in court. We don't want that to happen. And part of that is it's related to priming. I mean, subliminal priming is a kind of special case of this, but if we prime people with some construct, it can change their behavior, it can change their survey responses. So one of my colleagues at Stanford, her dissertation was on stereotype threat and driving performance. So she had people come in, and some of them she basically activated the concept of women, and that subconsciously activates this idea of women are bad drivers, and so it actually influenced their driving behavior in the driving simulator. So if we're going and we're running our study, we should ask people, what's your gender or sex after they do the driving, so that we don't activate the stereotype and the stereotype threat, because their gender or their sex is not going to change while they're driving the car. But asking them, priming them, that can change their behavior. So what we want to do is we want to avoid those kinds of things. We want to avoid the contamination of later measures. So sometimes you have to go and say, all right, I'm asking a bunch of things in my survey. Is question 1 going to contaminate question 2? So if I ask people something, is it going to change subsequent questions? Only Daryl Bem would worry about stuff at the end of the questionnaire influencing things at the beginning. And then you really want to run a pilot test, because for surveys, it's often very cheap and easy to do it. And you need to go and make sure that people are understanding the questions correctly. So something that might make sense to the survey author might not make sense to the people who are taking the survey. And you also want to make sure that you get actual and useful variance. So if everybody gives the same answer to the question, then your question's kind of worthless. So yeah, you don't want to go and have, or you don't want something where it's just like randomly distributed and you're like, I have no idea what this means because there's no the variance in it is not systematic. And if you have multiple items that kind of go together, you can use something like Cronbach's alpha to say like, all right, my set of items is reliable. These things fit together. Factor analysis is a way to do this after the fact, which is very clever. I'm not brilliant with factor analysis, but basically you're like, a lot of questionnaire measures are built by factor analysis, like John Besantzen Drury's trust in technology inventory. And you can say, oh, I have 20 questions and these 5 questions all relate to a certain construct or a subconstruct, and 5 other questions relate to a different one, and then the other 10 go together. And that's an entire area of research of like questionnaire design and developing these inventories and making sure that you're actually saying like, oh yes, under trust, there's like the goal alignment of this system. There's the actual technical capability. So there's these subconstructs, and factor analysis helps you to find those. Because there aren't that many people on the call, it's probably not that valuable to go and do an exercise, but we could go and make a survey of, and I was hoping to go and do a survey of how well this class works and how much did you learn. And we can develop that collaboratively as an exercise if people really want to. But if it's just Rashid and Sean, then maybe this is not necessarily a necessary project. And with that, I thank you for your attention.
Rashid, are you gonna say something?
Now,
Oh, sorry, it sounded like you were.
No, my deck is done. I'm happy to answer any and all questions if I can.
Yeah, I just it was interesting touching on the Bayes analysis. I have not done that, but I just was reading a paper that did it, and I was like, "What the heck is this?" It was like, "This is a totally different approach." I think one survey method that is not survey method, sorry, one research method that is probably coming up. And I best paper award at CSEW last year did this. They never ran hypothesis testing. They treated everything purely as predictive. So like, hey, can we predict blah? And then let's go run a follow-up and see how well it predicted things again. So it was more so like, we're not going to do hypothesis testing. We're using like basic machine learning, and that was how everything was constructed. So and then you get it, and it was the idea that when they they had the study, they created the model, and then they ran another study with the model again. How accurate was the model, and then how did people feel about it, and that was it.
That's becoming even more of an accepted model. So there's nothing wrong with an exploratory study where you're not putting out your hypotheses ahead of time. This is becoming more of an issue with psychology because of the replication crisis, where a bunch of seminal studies, people go and they try to replicate them and they don't replicate. There's also the cases of outright fraud, like Daryl Bem and Diederik Stapel, who just made up all their data. And so it's like, wait, is this thing not real because the people who did it just committed fraud? But even the real studies like subliminal priming, does that actually hold up? And the answer is not as well as they thought. So nobody committed misconduct, but is it real? So to Sean's comment about the exploratory study, so we could either go and we say we have these hypotheses and we're going to try to falsify them. The other model is we could just see what comes out of it. And the problem with that, if we want to call it a problem, is we can't necessarily demonstrate causation that way. In that we're basically saying, like, especially most of the machine learning things where we're basically looking at correlation. So A and B occur at the same time. We didn't do anything to cause it, to cause B. So, but that you can get around that by saying, okay, we're going to do an exploratory study first, see what things go together, and then we can go and run subsequent experiments to go and be like, aha, the arrow of causation points from A to B.
Yeah, and I've seen what they'll do with those, the ones that are really good, usually have a lot of qualitative evidence to back things up. And they're usually leaning much more towards external validity.
Yeah, there's definitely a lot of, in terms of the validities, like balancing your internal and external and, trying to balance your internal and external validity. So like when I've been doing my research, it's like, okay, do I go and try to look at optimizing my internal validity and or my ecological validity? Can't, there's something, it's not always a trade-off, but it's often kind of a trade-off. So I'm like, okay, I have, so in my dissertation work on the moral conflict, I improve my ecological validity by putting people under time pressure, but I have only one trial. I have one order of things happening that kind of hits me on internal validity. Other people go and they're like, okay, we're going to do this thing and we're going to get more internal validity, but it's not a real situation. So
Yeah, I've had it where I've had a study we just could never get published because it had good external validity, but we traded like it was such a naturalistic study you couldn't really do anything, and like the scenario and the place we were doing it was very unique and novel, but reviewers never cared enough about that, so it could never bump it over the edge.
yeah, these are problems that are like, some journal editors are going to say, I want more ecological validity, and some might say that they're more concerned with internal validity, and you can kind of get stuck.
Yeah, that's one of the, I think in the fields that we're in, which are so interdisciplinary, it's one of the most difficult things is that the reviewers you come across is like, what do they value more? So, and it's hard when you are a reviewer because you have to reduce your own bias. You have to be like, oh, okay, like what are they setting out to do, and did they do it? Because I have reviewed papers where I'm like, there's almost no external validity here. Like this is like in a lab and everything's so particular, and there's no discussion around any type of broader meaning. So it's like, oh, okay, like that's great, but this was such a specific thing. Like, what is the grander point or next step? which usually, like, if you go and have a really good discussion around it and you can tie it into other research and then expand upon how, like, you could do further studies, like, I've seen that work. But when it's just pure internal validity, it's like, oh, okay, like, what's going on? So, and I've had people in our group where their entire thesis was basically taking something out of an in-lab study and putting it in the wild. And then basically they're judging how much internal validity do they still keep compared to the in-lab study. And I've seen a lot of people, like, that's kind of what they do for their research, which is great because then it expands the number of participants, but it also, like, by bringing something out of the lab and making it easier to do in any setting, if it is beneficial to somebody, it's then easier to help people.
Yes.
So it's a narrative that almost writes itself. But I love that you brought up the ecological validity, like that term, because usually I always just think of it as external.
Yeah, I mean, some people will
Yeah.
use those interchangeably, and some people will come after you. But that's not a fight that I think is worth fighting.
What's the point? It's like they're just synonyms. Just be aware.
Yeah, I mean, there's some article where they're like, these are not synonyms. Like, there's some like technical splitting hair thing, but I don't want to go into that.
Yeah.
But the real thing for the TV audience here is that when you're designing your study, you've got to be mindful of how much can you get as much of both of these as you want, and then you have to worry about trading off. So I have some colleagues who did another moral decision study, and they have a really great simulator. They go and they drive down the road, and then they have to make a choice between a probability of killing themselves versus killing somebody else. But the way they set this up, time stops. You've got discrete probabilities on your screen, and you can toggle through your choices that way. So it's like, all right, time has stopped. I have a 25% chance of dying if I go to the left, and the other person has a 100% chance of death if I go to the right, A or B. Now that basically shoots your ecological validity, because in real life, you don't have infinite time, you don't have probabilities to examine, but they get quite a lot of internal validity. My study is the opposite. I'm like, all right, I'm going after ecological validity. So I'm introducing a whole bunch of uncertainty in my study, where people are driving down the road and they have 3 seconds to make this choice, and there's a continuous outcome, and everybody has their own assessment of how scary the various things are. And so it's like, all right, I'm throwing everything in the ecological validity side at the expense of a bunch of internal validity.
Yeah, that's a great example. Yeah, the biggest thing that came up in my mind with that example, so with the study that had good internal validity, the first question in my mind is like, well, the person who's going to be hurt, who are they? Are they like a stranger, a family member, a friend?
That was one of the variables in their study.
Okay.
And so they systematically varied that. So it says like, this is your friend, this is your child, this is, I think I'm getting this one correct, that they were systematically modifying probabilities and who the other person is.
Mm-hmm.
There's certainly another study that I criticized in my work, where they had a repeated measure study because they wanted to get more out of participants. And so you're driving a train and you can control the switch, and it's paired comparisons of victims in a trolley dilemma type situation.
Mm-hmm.
And so the thing is that if you know that there's going to be 10 trials, you will change your behavior to equalize the outcomes. So you're like, okay, there's in one of the conditions, there's a white man and a black man. And so it's like, okay, I hit the white man first, then I hit the black man, then I hit the white man, then I hit the black man, and I end up with 5 and 5. And the experimenters are not going to think that I'm a terrible person. And so if I'm the editor, I'm going to say, well, I like that you did this in virtual reality. I don't like that you had a repeated measures design, because you then have people going and equalizing the outcomes to so that people can cover up their social desirability bias.
Yeah.
They did account for this. So they said, okay, well, we'll do another analysis where we'll only analyze trial 1. And so it's like, okay, what do people do in their first trial before they can equalize their outcomes? But if they still know that there's going to be 10 trials, then they're like, okay, well, it gets into this question of, are people showing their true behavior when they're like, okay, I have to make a choice for trial 1, but not, but I can go and undo my show of bias in the next trial.
Yeah.
So, yeah, this is like one of the hardest pieces of your study design, where you're like, okay, I'm going to have to go and be like, I have 1 trial per participant. This is going to cost a lot of time and money. I'm going to have multiple trials. That gives me better statistical power for a lower cost, but then my validity gets killed.
Yeah. I think in my experience, it's always the idea of like, you need some minimum of each to be like, yeah, okay, that's like,
Yeah.
that's enough. And but it harkens back to your original point of like, you try and get as much of both as possible, and then eventually you get to the point where you have to decide on trade-offs. So, but anyways, I have to put a little girl to bed. Great talk, Dave.
Yep,
Thank you.
If there's anybody else out there in TV land, if you have any other questions, please ask. Otherwise, I'm going to shut down the stream, and that'll be that.
Awesome. Thank you so much. Be well.
You too.
It was a nice session. Thank you.
All right. Thank you, Rashid. Thanks for staying up quite late for this. I appreciate that.
Sheesh.
All right. Have a good night.
That was it. Okay. Have a good rest of your day. Bye-bye.
Bye.